Hi, so we'll do a very brief introduction to binary search trees before we get into all the implementation details. So here are some reasons we want to study binary search tree. So one of the most common operations that we can do in any data structure is looking up a piece of data and see if it exists in that data structure. Right, and we've studied a couple search algorithms such as linear search, which we know is very slow, on the order of n, but binary search and is a lot faster on the order of log of n. So for a data structure that has, say, 1,000,000 items, binary search takes 20 comparisons to find the data, if we can use binary search, right? So the problem with binary search is obviously, it requires data to be sorted, and sorting something can be very slow. And as we've already seen in one of our data structures, the ordering list, in order to keep things sorted, the insertion and the removal, they're both linear, order of n. So the question very naturally is that then can we get the best of both worlds? Can we have a data structure that can do insertion, removal, and search all in log of n? And the answer is yes, we can have a data structure like that. And this is one of those. It's a specialized tree called a binary search tree. So binary search tree is a data structure or a abstract data type, whatever you like to call that, that is satisfy a set of invariants. So what invariants are? Invariants are just conditions that are true before and after any sort of operations on the data structure. Okay, so let's see what the invariants are. So first we look at binary tree, not binary search tree. Okay, so a binary tree is very simple. It's a tree, obviously, and the only other invariant it has is every single node in this tree has at most two children, right? A left child and a right child. So you can see, for example, the root has two children, this node has only one children, and this leaf node has no child, obviously. So now binary search tree kind of by itself is not terribly useful, but it does, it's one step closer to the binary search tree. So what a binary search tree is, obviously it has to be a binary tree that it has at most, each node has at most two children. Now, the next two invariants are the most important, so read that very carefully. Basically for each node X, every data. Now, sometimes other literature refer to data to as keys, and actually I would prefer to use key as well, but the reading use data, so I don't want to add any more confusion to it. Anyway, so for every node X, every data on the left subtree of X must be less than what's in node X. So as you can see here, every data in the left subtree of 10 is smaller than 10. And then if you check all the other nodes, that condition holds. And then by the same token, or kind of on the flip side of this, is then every data on the right subtree must be greater than the data in X. So you look at all the numbers in the right subtree of 10, they're all bigger than 10. Okay. And just a couple notes that, we talk about binary search tree, and we often abbreviate it as BST. And another thing about our version of BST is we don't allow duplicates. Most implementation probably don't, but some do. And finally, it should be obvious, given that the binary search tree has more invariants than a binary tree, then every binary search tree is a binary tree, but the converse is not true. Okay, so enough talk. Here is a little bit of exercises for you that look at all of these trees and identify the one that is a binary search tree. All right, so as you think through it, hopefully you thought through it and you see that none of these trees are a binary search tree. The first one obviously has more than 3 children under the node 3, so that's not binary, not even a binary tree. The second tree has at most 2 children per node. However, on the let's say for node 6, the left subtree should be smaller than 6, but the left subtree has 20. And as a matter of fact, every single node in this tree violate that condition. It's a binary search tree, but flipped horizontally. The last tree might be a little subtle, but it also kind of illustrates what you have to check when you check for if a tree is a binary tree, is that every single node, the right subtree must be bigger and the left subtree must be smaller. So most of the nodes in this tree satisfy the condition except this number 40 here. So 40, if you check the node 42 up here, 40 is inside the right subtree of 42, but it's smaller than 42 rather than bigger. So this is also not a binary search tree. And we'll get into implementation very soon. I just want to give an overview of how most of the implementation is like, because they all follow a certain kind of pattern. And so the logic for that is, if we look very closely, for every single node, every left and right subtree, they are also themselves binary search trees, right? So for example, 10, if you look at the left subtree, I mean, this is a binary search tree. You look at the right subtree of 10, that's a binary search tree. If you look at, let's say, the tree rooted at 38, its right subtree is yet another binary search tree. So many of the operations in binary search tree kind of very naturally lends themselves to recursion, because we start with a big tree, we recurse down to the smaller tree, but doing the same thing. Now, just want to say it is actually possible to do everything iteratively, but it's a lot more complicated, less elegant, and it usually requires us to manually maintain a stack or a queue. But as you all know, recursion kind of implicitly maintain a stack for us, which kind of why recursion makes implementation of many of the operations very, very elegant. And so what do most of the operations going to look like? You will see many examples of this as we go on, but I just want to give you an overview. So most operations, they will have some base case, like any recursion. So the base case could be the tree is empty. Well, then it's obvious. It's probably, we probably know right away what the answer is, right? And also, then the operation would perform some sort of recursive operations on both the left subtree and the right subtree, and based on some conditions and that kind of things. And then finally, most of these operations actually have a pair of methods. One is a public method, and that public method usually just deal with data. And the public method is used by client code, so they don't really pass in the root of the tree, right? Because the root of the tree is kept track of by the tree itself. But the public method would call the recursive version and bootstrap the recursive version with the root. And then obviously the other version of most operation is the private and recursive method. And it always takes a subtree and work with it. Okay, So yeah, keep that in mind as we start talking about the implementations.